Hello, my name is Jonah Bartrand, and I'm a master's student working with Dr. John Bradford in the Department of Geophysics. And my thesis focus is using aerial GPR, ground penetrating radar, to survey snowpack and to determine snowpack quantity and quality. So aerial GPR is ground penetrating radar mounted on any sort of aerial platform. In particular, I'm focusing on GPR mounted on drones for use in surveying snow, and drones are a perfect application for GPR platforms over snow because of the low contrast. So we actually get penetration down into the snow, and surveys are much faster and safer. One of the issues that I'm going to be addressing is with the precision of the GPS chips that are typically included with mid-level drones. So on a typical ground survey, there are two types of survey methods that can be done with GPR. One of these is a common midpoint, where your transmitter and receiver are moved progressively apart about a common point on the ground. And this type of survey can give you information about subsurface reflectors and about, more importantly, the velocity in those different layers. Common offset data is much quicker to gather because the receiver and transmitters are fixed relative to each other, so they're not moved apart. And you can collect a lot of data just dragging a sled or flying a line. But there's less information included in the data. You don't get direct information about the subsurface velocity. And this is a problem when we're talking about snow, because the snow traits can be inferred from the velocity. But we can use diffractions that are present in common offset data to get some idea of what the snow velocity is, at least in particular locations where there are diffractions. So here I've got 3 diffractions shown, and a diffraction occurs when we've got reflections off of a point source embedded in the subsurface. And we can see that the tightness of the diffraction is related to what the velocity is. The tighter the diffraction, the lower the radar velocity. But when we've got issues with our horizontal trace locations, then the diffractions can get messed up, and we can see that with a progressive amount of error in the horizontal location of the traces, we have substantially more error in the diffraction shape, which affects the determination of the velocity from that particular diffraction. Here, the most error shown on the right is a 5 centimeter standard deviation error. Most GPS chips for drones have an error of about, on the order of a meter. So that's a big problem. But because we know the shape of the diffraction, if we know where the scatterer is and what the overburden velocity is. With aerial GPR data, the overburden velocity in the uppermost layer is known because we know the velocity of radar in air to be 0.3 meters per nanosecond. So if we see a diffraction that originates at the ground surface, then we can use this diffraction to establish relative trace locations using this formula shown here at the bottom, where x is the distance from the apex of the parabola, or hyperbola, I'm sorry. So here I've got 2 different radargrams shown. The one on the left would be data that we go out and collect, and we don't have a good constraint on what the horizontal trace locations are. So we see that we've got irregularities in the diffraction wings. And these irregularities are going to cause issues with the certainty of our velocity estimates and can actually change the velocity as well. So if we take the trace that corresponds to the apex of the diffraction and we cross-correlate that with all the other traces that contain subsignal of the diffraction, then we can establish a relative two-way travel time that we can then plug into that earlier formula and establish relative trace locations from the apex. So that's shown here in the lower left, where the true trace spacing, relative trace spacing. So this is showing the value plotted here is the difference between the n trace and the n+1 trace. So it's not showing the absolute location, it's showing the location of each trace relative to its neighbors. And the true trace locations are plotted in green. And then if we assume a uniform spacing, then each trace we would assume would have an equal distance from all of its neighbors. So that's shown with the flat blue line. Then if we apply our location recovery algorithm using that cross correlation and the formula shown earlier, then we get the trace location values shown in orange. And we can see that we do a pretty good job in most places of recovering something pretty close to what the true trace spacing is. And if we look in the lower right, we should plot the absolute error between the true trace spacing and the recovered trace spacing and the assumed. And we see that almost everywhere the error for the recovered trace spacing is much lower than the error for the assumed trace spacing, except at the apex of the hyperbole, of the apex of the diffraction. This is because the sensitivity of the diffraction move out to changes in horizontal location at the apex are very small. That's why we see a relatively flat top on the diffraction. So if the sensitivity is low, then accurately recovering that horizontal location is going to be very difficult. So how does this relate to snow? So I've generated a very simple synthetic snow model, as what we might expect to see. So the velocity model on the left shows an error layer of 0.5 meter thick, and then we've got a constant velocity snow layer beneath it, and then we have the ground interface with a much lower velocity at the bottom. And for this case, data that we see off of the ground isn't going to matter. And I've also embedded two high contrast pixels in this model to produce those diffractions that we would expect to see. And on the right is our synthetic radargram generated from this velocity model, with assuming a common offset of 0. And we see that the strongest signals in this radargram are actually the horizontal reflections off of the interfaces. And because we want to focus on the diffractions, I'm going to apply a background subtraction to remove most of those reflections. And that's what we see here. So on the left is that original radargram with the true spacing, and we assume that and we've removed those reflections so that those diffractions show up much clearer. And I've also plotted those the apexes of those diffractions, the red corresponding to the surface diffraction, which we're going to use for our trace location recovery, and then the white for that embedded diffractor in the snow that we're going to use to try and recover the snow velocity. So I've then randomly subsampled that true spacing radargram and then assumed a uniform spacing to generate the assumed spacing radargram. This would, again, simulating that error in our horizontal location. Then I've applied our trace spacing recovery algorithm using that upper diffraction, because we know the overburden velocity is that of air, to produce the radargram on the right. And we see much smoother diffractions. And the lower two plots show the semblance curves calculated at those apex locations. And there's a lot to get into with semblance curves. The important thing to know is that where we see a peak semblance value, that should correspond to the velocity, the Dix velocity in that layer. So for the surface reflection at apex 1, surface diffraction, excuse me, for the surface diffraction, we should see a velocity of 0.3 because that's velocity of radar waves in air. And we see that match for the recovered curve in green and the true curve in blue. But it does not, the peak value for the assumed semblance curve does not match. It's lower, and that peak is also broader, which indicates more uncertainty. And this same thing is true for the apex 2, the embedded apex in the snow. So because I generated the velocity model, I know what the snow velocity is, and the peak semblance values for the true and recovered curves match, but the semblance value for the assumed radargram does not match. It's lower and it's also broader, again, indicating more uncertainty in our estimates. So this method is very valuable for applications where we don't have good geolocation, but we do have scatterers on the surface that produce those surface diffractions that we can use to determine relative trace locations. So this is important for getting accurate velocity estimates for the subsurface embedded in the snow, which we can then use to determine snow depth, but also snow density, and ultimately total sweet content. Thank you.